Next topic is encoder design. So, the conversion of time varying analog signal of with an audio signal is an example for the that has to be converted into digital form is carried out using an electronic circuit is called as signal encoder. So, encoder in the sense the conversion of time varying analog signal into a digital form using an electronic circuit. The principles of encoder is this is the principles of encoder. Here we can see that two main circuits are used in the diagram in this encoding design. One is called as a band limiting filter, another one is called as an analog to digital converter ADC. Band limiting filter and ADC, which comprises of sample and hold circuit and a quantizer. ADC which has sample and hold circuit and quantizer. So the typical waveform set of signal encoder are shown in the figure. The role of a band limiting filter is to remove the selected higher frequency components from the signal source A. This is the signal source A. The band limiting filter role is to remove the selected high frequency components from the source signal. The output of the filter is then fed into the sample and hold circuit. The name itself implies that it is used to sample the amplitude of the filtered signal at the regular time intervals. And to hold the sample amplitude constant between the samples. Constant between the samples. This in turn it is fed into the quantizer circuit which converts each sample amplitude into binary value is called as code word. So we have band limiting filter and ADC. Okay, band limiting filter is used to remove the selected high frequency components from the source signal, and output of the filter is fed into it is given to the sample, that is ADC converter circuit, which comprises of two components. One is nothing but a sample and hold circuit, second one is called as quantizer. So sample and hold circuit used to sample the amplitude of the filtered signal at regular time intervals. Okay, so like that it filters the samples regular time intervals and use it to hold the sample amplitude at constant between the samples. In turn, the quantizer, which converts the sample amplitude into binary value, is known as code words. The most significant bit of each code word indicates the polarity sign of the sample, that is 0 means positive, 1 means negative. 0 or negative relative to the 0 level, positive or negative which is related to the 0 level. Normally the binary values indicates positive value for 0 and binary 1 indicates negative value for the particular bits. To represent the amplitude of the time varying signal precisely requires first the signal to be sampled at the rate at which is higher than the maximum rate of the change of signal amplitude. Then the number of different quantization levels to be used as large as possible. So two techniques are there, one is sampling, another one is quantization. So sampling in the sense, according to the sampling rate Nyquist sampling theorem, to obtain this Nyquist sampling theorem, an accurate representation of time varying analog signal, the amplitude must be sampled at a minimum rate that is equal or greater than twice of the highest sinusoidal frequency component, that is f is equal to 2f. That is called as Nyquist rate. That means the amplitude must be sampled at minimum rate that is equal to or greater than twice of the highest sinusoidal frequency component that is present in the signal is known as Nyquist rate, normally represented as either in hertz or it may be represented as samples per second, SPS. The sampling a signal at a rate which is lower than the Nyquist rate results the additional frequency components that are being generated not present in the original signal. So this signal causes the distortion. That means the original signal to become the distorted. This distortion caused by the sample signal at rate lower than the Nyquist rate, considering the effect of undersampling. So in general we can say that all frequency components present in the original signal that are higher in frequency than the off-sampling frequency in hertz will generate the lower frequency alias signal, which simply add to those making of original source signal, thereby causing it to become distorted. However, by first passing the source signal through the band limited filter, which is used to design to pass only those frequency components that are determined by the Nyquist rate. Any higher frequency component in the signal which are higher than this removed before signal is sampled, higher than this are removed before the signal is sampled. Because of this function, the band limited filter is also known as anti-aliasing filter. It is also known as anti-aliasing filter. In practice, we can say that the transmission channel used or available often has a lower bandwidth than the source signal. So such cases, in order to avoid the distortion, it is the bandwidth, the frequency range of transmission channel that determines the sampling rate rather than the bandwidth of the source signal. So in such cases, the source may have the high frequency components that is deducted by the Nyquist rate of the transmission channel. It is first necessary to pass the source signal through the band limiter filter and designed to pass only the sinusoidal frequency components which are within the bandwidth of the transmission signal is called as undersampling. Next one is quantization. Quantization in the sense to represent the digital form of the amplitude, the set of analog samples are shown here. This is analog samples. This is analog sample, and according to that the binary codes or samples are taken, and then each sample is represented by binary code word. Then quantization is nothing but approximating the samples, then writing the code word. So to represent the digital form of an amplitude of a set of analog samples would require the infinite number of binary digits. When a finite number of digits are used, each sample can be represented by corresponding number of discrete levels. The effect of using finite number of bits can be seen considerably here. It is seen here. So this results 4 positive and 4 negative quantization intervals. The two magnitude bits are determined by the particular quantization interval. The analog input signal is at the time of each sample. So if V maximum is the maximum positive and negative signal amplitude, then N is the number of binary bits which is used. Then the magnitude of the each quantization interval Q is equal to 2V max divided by 2N. So here the signal anywhere within the quantization interval is represented by the same binary code word. That means each code word contains nominal amplitude level which is at the center of the corresponding quantization interval. So hence the actual signal level may be differ from the by up to plus or minus q by 2. The differences between the actual signal amplitude and the nominal amplitude is called as quantization error. What is quantization error? The difference between the actual amplitude and the corresponding nominal amplitude is called as quantization error. The quantization error values are expanded normally will vary randomly from sample to sample, and the noise which is created in this error is called as quantization noise. The noise which is created in the error is called as quantization noise. The term noise is being used as electrical circuit which is referred to the signal whose amplitude varies randomly with respect to time. Another related factor which influences the choice of numbers of quantization intervals used for the particular signal is smallest amplitude relative to its peak amplitude. With high fidelity music, it's important to be able to hear the very quiet passages without any distortion created by the quantization noise. The ratio of peak magnitude of the signal to its minimum amplitude is known as dynamic range. So dynamic range is nothing but the peak amplitude of the signal to the minimum amplitude. That is represented as D. Normally it is quantified using logarithmic scale. Hence, when determining the quantization intervals, the number of bits used, it is necessary to ensure the level of quantization relative to the smallest amplitude is acceptable. So, this is nothing but encoder design. Thank you.